So here is the outline of this chapter. So we'll introduce the capacitance, and then we'll try to calculate capacitance with different structure, and also introduce the parallelism and the serial of the capacitance. And then energy stored in the electric field. This part is a bit more difficult, which is about the dielectric, which is somehow related to the some hardcore physics. But actually, if you don't really care about it, it's fine. You just need to substitute the correct value in the Gauss law, and everything will be fine. So this is a capacitance. The definition is it consists of two isolated conductors or plate, or usually plate, with charge plus Q and negative Q on each side. So its capacitance C will be defined as Q equals CV, which means that for a given structure, then the capacitance should be a constant, and then if you provide a larger potential difference between the two plates, and then there will be more charge accumulate at this capacitor. So it is proportional, a linear relationship. So actually we have learned how to calculate the E field between two infinitely large plates. So suppose this plate and this plate are infinitely large, and then placed close together. You know that the E field in between will be constant. So it starts from the positive plate to the negative plate. However, the capacitance can't be infinitely large, so we will assume that in between the two plates there will be approximately uniform E field. So actually this side will be more dense, and then this side will be a bit sparser. And actually, outside the plate, there will be some E field lines like this, and actually like this, like this. So we will at least assume the E field in between the two plates are uniform. So here, this is a setting. We have a battery here, and then this is a switch, and then this is a capacitor, at least two conducting plate. So drawing it in the electric symbols, a battery is look like this. So this long edge is a positive edge. This is the negative edge. So the potential, electric potential at this point would be higher than this point, and then this stands for the switch. This stands for the switch, and the capacitor is simply drawing two parallel lines. This will stand for a capacitor. So when a circuit with a battery, an open switch, and uncharged capacitor complete by closing the switch. So at the very beginning, this switch is open, and then it is short at the moment, and then there is some charges, positive charge go to this side, and then negative charge go to the other side. So the battery maintains potential difference V in its terminals. So as you know, battery So the terminal of the higher potential is labeled as plus. Usually we will not actually write the plus or negative because the long side already means that side is positive. So as mentioned, we have already learned that how to calculate the E field, and we will assume that in between the plate there will be uniform E field. So if we have a capacitor like this, and then this red dotted box is the Gaussian surface. So we apply the Gauss law according to this Gaussian surface. So we have and actually in chapter 24 we know that the potential difference is the line integral of the E field, and then take the minus sign. And actually in this figure so we have the initial point here and then the final point here. Initial point at the negative plate and the final point at the positive plate. So ds is pointing upward. ds is pointing upward. So it is opposite to the E field direction. In that case, E dot ds will be a negative number, so it will cancel this negative sign. So this is the reason why it assumes this is the I, this is the F, so that it will cancel the negative sign here. So here we have a V. V is actually the potential difference between F and I. Vf minus Vi. And then I is the negative, so we put a negative sign here and then a positive sign for the F. So EDS is parallel and in opposite direction. So E dot ds is minus EDS, and then the minus sign cancel. So we have this expression. So next, applying the Gauss law to this Gaussian surface, we have actually A is the surface area, the surface area of the capacitor, and then the E field is uniform. And then actually regarding to the bottom side, to this side. For the other three sides of the Gaussian surface, there will be no contribution because there will be no E field in the plate, in the conductor. There will be no E field, and then for here there will be no E field in this direction. No E field in this direction. So those two sides will not contribute EDA either. So only this side will contribute the net flux. So actually it is EA for this surface integral, and then epsilon naught EA on the left side, and then Q is the Q in charge. We assume all the charge are on the bottom side for this plate. So, and actually for this integral is still integrating the constant. So EDS integration is nothing but EDS, and then the D is the distance between this plate and that plate. So V is nothing but ED, so just integrating a constant. So here we have Q equals, let me see, E. So we have E equals V over D. So we have E equals V over D. And then we substitute this one into here. And then also, we already defined that Q equals CV for a capacitor. So that this one also substitute to the right side. So we have epsilon naught V over dA equals CV equals dV. So V and V can be cancelled. And it turns out to be C equals epsilon naught A over D. Epsilon naught A over D. This is the capacitance regarding to the geometric structure. So epsilon naught is the constant. We already know that it should be 8.85 times 10 to minus 12 with some SI unit. And then A is the surface area, so the SI unit would be m square, and then D is the distance, so the SI unit would be m. But for the capacitance, I'm not sure whether it is included there. The SI units. Okay, so let me mention it here. The SI unit for C for the capacitance is F. Farad. So I think it's probably a short form for the Faraday's. Actually, you learn the Faraday's law in chapter 30, chapter 30, which is one of the Maxwell equation. And actually, for the capacitance, the SI unit is F, Farad. Okay, so far any questions? So far any questions? No questions. So next we consider another type of capacitor. Or maybe I can just tell you more about this parallel plate capacitor. Maybe if you learn the high school physics, you already know this expression for the C, but actually it tells you that if you hope to have a larger capacitor, which means the surface area will be larger, or you could place the two plates close together, then the capacitance will also be larger. So this is the point for changing the capacitance regarding to the geometric structure. So this is another type of capacitor, which is called a cylindrical capacitor. If you have ever opened the case of your computer, you may have find some capacitor like cylindrical shape, and actually that type of capacitor is very interesting. It can explode if you actually that capacitor is look like this, and then it has two footprints. One is longer, one is shorter, and actually for the longer footprint it should connect to the positive voltage, or at least this electric potential should be higher than that one. Otherwise, it will explode. It is very interesting. And yeah, so this is that type of capacitance. Actually, the capacitance value would be larger for this one, and it is used for rectifying the voltage or the voltage supply for the circuit. So here, the cylindrical capacitor, here is the cross section. So we will have the shell and then the inner coaxial. So a cylindrical capacitor of length L. So it is somehow like, so this is a cylinder, and then this is L, this is L, and then this shows only the cross section, So formed by two coaxial cylinders of radii A and B. So the shorter one is A, the longer one is B. So we assume that L is much larger than B, so that we neglect the fringing of the electric field. The fringing means this type. This type is called the fringing because it is not uniform and usually small. So we would neglect it. And here we assume L is much larger than B, so that the fringing effect will be negligible. So each plate contains a charge magnitude Q here. So still we apply the Gauss law for this Gaussian surface in red color. And in this case, actually the E field will be pointing outside because we assume that this one is positive charge, this one is negative charge. So the E field will be in radial distance and then point to the outside. So if we have a Gaussian surface here, we also have a dA in the same direction, so that the integration as E dot dA epsilon naught will be nothing but epsilon naught EA as before. So we have the Maxwell equation like this, and then A is the area of this side. So the height will be L, and then the perimeter, not the perimeter, yeah, the length of this circle, will be 2 pi r. So the area of this Gaussian surface will be, so the Gaussian surface is actually not only a circle, it is actually this way. So this is the Gaussian surface. So the surface area will be 2 pi r times L. If you cut it vertically and then expand it, then it will be a rectangle. So it is nothing but 2 pi r times L for the A. And then similarly, we have V equals integration of EDS from negative side to positive side. Let me see. So here, this is the negative side. This is the so this is I. This is or this is the. Yeah, so this is the negative side. This is the positive side, which means that ds is pointing to the inward, which means that E dot. So ds is from here. Is from B to A. Is from B to A. And actually, we integrate it with respect to R, and actually R should be minus S, because if you consider B is a positive value, A is a positive value, which means that R should be in the opposite direction. It should be in the opposite direction. R should be that way. So this is S, this is R. So in this case, we have an additional minus sign here. And then, of course, we substitute E. E equals Q over 2 pi epsilon naught L here. So we have this term to be here, and then we still have an R here. So r will keep in the integral sign because this is a variable, and then we change ds to dr. So r equals minus s, which means that dr is minus ds. So that to make this value positive, maybe that sign. So here a and b is positive value, and then integrate this one 1 over r. The antiderivative is a log function, the lateral log function. So lateral log of r evaluate at b and a, and then we also have a minus sign. So finally we have ln lateral log of b over a for this integral. And finally, we also have c equals qv. So q and q can be cancelled, and then we have 2 pi epsilon naught L, which is this term over lateral log of b over a. So this is the capacitance for a cylindrical capacitor. By simply applying the Gauss law to this one. So likewise, if you want to have a large capacitance, you need to make this capacitor larger L. This C will be larger. And then the other way is to make this term smaller, because it is in the denominator. So to make C larger, which means that you need to make this term smaller, or in the other way, that B should be close to A. If B is close to A, then this term will be smaller. We already know that B must be larger than A because this is the outer radii. This is the inner radii. We already know that B is larger than A. So B over A must be larger than 1. So lateral log of B over A must be larger than 0. But if B over A is smaller, then this term will also be smaller because lateral log is a monotonic function. Which means that if B over A is smaller, which means that these two coaxial cylinders are close together, which is similar to this case. If you want this capacitance to be larger, you can also place these two plates closer. Any questions? So this is the other case for a spherical capacitance, which is choosing the spherical capacitor. So still although the cross section is still the same, but actually this is a sphere. This is a cylinder. This is actually a sphere. Difficult to draw a 3D graph here. But actually this is the case. So actually you can also apply the Gauss law like this, but the term may be a little bit different. This may be 4 pi r squared rather than this area, and then we can repeat all the calculation. And maybe here is, I think E is not a constant, because when you consider this is a spherical, this is inverse proportional to R square, inverse proportional to R square. So E is not constant here. So in this case, the integration is not integrating this one. Rather than it is integrating something like 1 over R square, so that it turns out to be 1 over R. And then the expression will look like this. So actually you can try to do it yourself. It is not that hard. And yeah, as you can see here, the capacitance for a spherical capacitor is like this. So 4 pi epsilon naught is a constant, which means it should be 1 over 8.99 times 10 to the 9th power. And for this one, it is somehow like 1 over A minus 1 over B. C equals 1 over K, like this. So likewise, if we want C to be larger, so we want the denominator to be smaller, which means that A and B should be close, and then it will make C to be larger. And here is a special case. So if we have an isolated sphere, which means that we just make B tends to infinity. B tends to infinity means that this one take away. Just remove this outer shell. And then we let A to be capital R, so that this expression will be very neat. It will be nothing but 4 pi epsilon naught R. So it is only proportional to the radius of the sphere. And this really makes sense because if you make R to be larger, which means that you increase the surface area of the capacitors. Although this is strange because previously we assumed that capacitors should have 2 plates or 2 conductor plates close together, but actually for this one, we assume that the outer shell is infinitely large. We only have one conductor ball there, but it already is a capacitor. So here's a checkpoint. So for capacitor charged by the same battery, does the charge stored by the capacitor increase, decrease, remain the same? In each of the following situation, the plate separation. So for part A, the plate of the separation of a parallel plate capacitor is increased. So how does the capacitance change? Increase, decrease, or remain the same? So if you still remember, C is epsilon naught A over D. If you increase the parallel plate separation, which means if we increase D, how does C change? Increase D. Increase, decrease, or remain the same? Decrease. Okay, this is for part A, and then for part B, the radius of an inner cylinder of a cylindrical capacitor is increased, which means that for C. For B, C is, let me see, 2 pi epsilon naught L, 2 pi epsilon naught L, lateral log of B over A. So here we increase A. Increase, decrease, or remain the same? Increase. Yeah, increase. So for the third one, the radius of the outer spherical of the shell. So here we have of a spherical capacitance. C, for passage C equals 4 pi epsilon naught A B B minus A. So this one D increase, A increase. So for this one, the outer B increase. So this is 1 over K B increase. B increase. Outer spherical shell increase. Okay. Oh, sorry. It should be A 1 over A minus 1 over A minus 1 over B. It should be like this. Increase or decrease? Decrease. Yeah, because the second term becomes larger. I mean B becomes larger, and then the second term will be smaller. The second term will be smaller, so that the denominator will be larger, so that the overall C will be smaller. So they decrease. Okay, so far any questions? So let's take a look at a sample problem. So switch S is closed to connect the uncharged capacitor of capacitance C to the battery of potential difference V, potential difference. So we have V for this. So we have this is positive, this is negative. Yeah, so the thickness is L, and the phase are A, and it consists of copper, in which the density conduction of the electron is N. From what depth D within the plate must the electron move to the plate face as the capacitance becomes charged? So this is quite a hardcore physics question, because if you zoom in this plate, so this is a plate like this, and we know that all the charge must go to the surface. And actually, if we have two plates playing close together, all the negative charge must be on the top surface. But actually, the thickness of the electron can't be zero, because the they should at least occupy some spaces. And then it tells you that the density is like this, and then it asks you how thick the electron should occupy. So here, first we can calculate Q equals CV. So C is 0.25 microfarad, and then V is 12 volt. So so this is 3 times 10 to minus 6 coulomb. Yeah. So this is the total charge on the plate. So there will be a positive Q on the top plate, and then negative Q on the bottom plate. And then it tells you that the plate has a thickness, but actually this number is not so related to the solution. And the face area, the area is A, and then the density could be N. So it is like, so first let us just calculate how many total electron for this charge amount. So we divide this number Q by an elementary charge, which is like 3 times 10 to the minus 6 over 1.6 times 10 to minus 19. So that we can count how many electrons are there. And then it would be 1.87 times 10 to 13 power electrons. So of course, this is D, and then the surface area is A. So that the volume of this, the volume should be A times D. So this is the volume. And then you multiply by the N. N is the density. So this is the density. This is the volume. So this should be N. This should be capital N. So we already know small n, capital N, and A. So we only want to find D, which is N over NA. So N is a 1.87 times 10 to the 13 over N is 8.49 times 10 to the 28th power, and then A is 2 times 10 to the minus 4th. So it turns out to be 1.1 times 10 to minus 12 meter, which is very thin. So, or you can write it as 1.1 picometer. Picometer. Because if you can imagine the radius of an atom is like 100 times larger, or that level. So 100 times, or and 100 times larger. So the thickness of the electron is very, very short. Okay. So here we talk about some simple calculation about the capacitance, which is the parallel and series. I think you should learn it in high school, I think. So for parallel, So suppose we have three capacitance here. Suppose we have three capacitance here, which is denoted by C1, C2, and C3. And then we have a voltage here. We connect all the positive side together, and then we connect all the negative side together. So this is called a parallel. This is called a parallel. And of course, C1, C2, and C3 might not be equal to each other, so that the charge goes to this plate, and this plate might be different. So we denote it as Q1, Q2, and Q3. Okay, so the Q, we want to hope CEQ is an equivalent capacitor, which means that we remove these three capacitors and replace by CEQ, and this charge should be the same as the total charge here, Q1 plus Q2 plus Q3. So this is a kind of conservation of charge. So independently, we have Q1 equals to C1 times V. V also shares because we directly connecting these four nodes together, so that they share the same V. In this case, Q1 equals CV1. V is shared. V is shared. So we have a Q1 equals C1 V1, Q2 equals C2 V2, Q3, and then it's substitute into here. So finally, we have a Q equals this one multiplied by V. If we have an equivalent CEQ here, it should be like a Q equals CEQ times V. So comparing these two, we have a CEQ equals C1V plus C2 plus C3. So it's nothing but adding all of them together for the parallel capacitance. If we have if we have n capacitors, then we just add all of them together, which will be the equivalent parallel capacitance. So for series, it is a little bit different. So here, we have a battery, still have a voltage V here, and then we connect the capacitor back to back. So it forms only one loop here. So actually, because if you don't have any battery here, this node should be electrically neutral, which means that the total charge at this node should be 0. So after you connected the battery, the charge amount won't change because there are no charge can go in this region. So it turns out to be that we have positive Q, negative Q for the first capacitance, and due to the conservation of charge for this area, this should be positive Q, and in this case, this is negative Q. And for the conservation of charge for this area, this is negative Q, so this is positive Q, and turns out this one should be negative Q. So Q is shared. So Q is shared. And here we also use the fact that the potential difference for the first capacitor is V1, V2 for the second one, V3 for the third one. And V is the potential difference from the battery. So that in the next chapter or in chapter 27, I'm not sure. So we already use this one known as the KVL, the Kirchhoff voltage law. Maybe you have learned it in high school. Actually, we have a Kirchhoff current law and Kirchhoff voltage law for for solving electrical circuits, simple RLC circuit. So we use this fact V equals V1 plus V2 plus V3, and then we substitute these three into here. Actually, the Q is shared. So V1, V2, V3 are different. So we have Q over C1, Q over C3. So substituting here, and then we can factor out Q so that we have 1 over C1, 1 over C2 plus 1 over C3, all multiplied by Q. So equivalently, also we have this expression, which means that Q equals CV. Q equals CV, yeah, Q equals CV. So V equals Q over C equivalent, something like this. So in this case, comparing these two, we have this one equals to 1 over C EQ, which means that C EQ is 1 over this term. Or yeah, so you can write it like this, or you can write it like this. And if you have n capacitor, the inverse of the equivalent is equal to the sum of the inverse of all the capacitance in series. So maybe you are familiar with a resistor. So for resistor is the other way around. For series resistor, R equivalent is R1 plus R2, and then for parallel capacitor, parallel resistor, R EQ would be 1 over R1 plus 1 over R2. So if you have only two, it will be nothing but R1, R2 over R1 plus R2. So this is for two resistors in series or parallel. For this case, CEQ, if you have only two, it is nothing but C1, C2 over C1 plus C2. If n is 2, this is all lowercase. But C and R is different. Simple addition for series R, but here simple addition for parallel C. Parallel C, we can simply add them together. But for parallel capacitance, we need to take the inverse, add them together, and take the inverse again. For the parallel R, we take the inverse of the resistance and then add them together, and then take the inverse again. So this is a series and parallel capacitance. So let's have a 10 minutes break.